Good afternoon and welcome to today's HydroCAD webinar. My name is Peter Smart. I'm the developer of HydroCAD and I'll be presenting the session this afternoon. Today we're going to be talking about dam breach modeling in HydroCAD. A dam breach is a new type of outlet device that was added in HydroCAD 10. There were actually a number of new outlet capabilities added, but the dam breach is perhaps the most significant. And we're going to be talking about that capability today, how you would set it up in HydroCAD, how it will integrate with the rest of your HydroCAD model, and how it combines with some of the other, or compares with some of the other dam breach routing capabilities that you may have used before. I want to start by talking a little bit about the basics of exactly what we're modeling from a physical standpoint. And a couple of sources I'd point you to. One of them would be the HydroCAD Owner's Manual. HydroCAD 10 Owner's Manual, page 95, has got a section on dam breach modeling. Also, if you open the HydroCAD Help System, and you can get there just with the Help button inside HydroCAD, and on the Index tab, go to Dam Breach, and you can come down to Dam Breach Calculations, and that will give you essentially the same information. So it's available in several sources. There is also a detailed page on our website covering dam breach modeling. So there's several different sources that you can go to get the information. What I want to use at the moment, I think, is just the page from the HydroCAD Owner's Manual, just because it's the easiest to view for the session. And let's talk a little bit about exactly what we're modeling here. A dam breach is essentially a weir. It's an outlet device on a pond that we're modeling. But unlike a normal outlet device, which has a fixed shape and dimensions, a dam breach is a failure in the dam. So it represents an opening, a weir, which is increasing in size. And the way we're representing this is essentially as a rectangular or a trapezoidal opening. So if it were rectangular, then we might be modeling a rectangular weir of this shape. Or it could be a trapezoidal shape, approximately like this. They're both variations of the same weir equation. It's just a matter of whether or not we're sloping the sides. And that is this total included angle, the notch angle. If that notch angle is 0, then it means we have vertical sides and we're simply modeling a rectangular shape. Now, the weir breach or dam breach will always begin at the top elevation that we specify, and then the breach is going to progress downwards over time. And so we will be specifying this elevation at the top where the breach begins, and we'll be specifying the height of the breach, and equivalent way to specify that is the bottom or final elevation that it will attain. And so that's the progression as the breach forms. The bottom width of the breach will remain constant as the breach progresses. And you can see that in this progression of rectangular or trapezoidal breaches here. So that bottom width, which can be 0 if this is a V-shaped breach, but whatever the bottom width is, it will remain constant. The breach will progress downward through the dam wall. And if we have specified a notch angle here, then the top width obviously is going to increase as it gets deeper. So that's the basic shape, and that's the shape that is most commonly simulated in dam breach scenarios. The progression starts based on two separate mechanisms that we can select. We can specify in HydroCAD that the breach will start at a specific time during the routing, so we could indicate that at 14 hours in our routing the breach will commence, or we could indicate a water surface elevation where we want to trigger the breach. So if we want the breach to initiate when the water gets up to a certain level in the pond, then we could set that water surface elevation, and the model would detect when that level was attained and initiate the breach at that time. Regardless of how we trigger it, the height of the breach increases linearly over a time that we specify. So we would specify the time to fully develop. So perhaps we'd have a breach that triggers at 14 hours and develops over the next 2 hours. So at 14 hours we would just start, we would initiate, and then after 2 hours we would be fully developed at 16. It would be similar if we specified a specific water surface elevation to start at. It would start at that elevation and then progress over the 2-hour duration that we'd specified. Because we have a varying weir here, the dimensions are actually changing constantly during the routing. We can't do this routing calculation using the traditional storage indication method. We have to use the dynamic storage indication method in HydroCAD. And when we use the DSI procedure, this tells HydroCAD to reevaluate our stage discharge curve at every time step during the routing. So this is what's used in order to account for the fact that the dimensions of the breach are actually changing. One more note on the physical layout of this is that what we're modeling with a dam breach outlet is just this breach cross-section. We're not modeling in this any flow over the overall spillway that might exist in the pond. So for example, if we had a spillway that was up here and our breach represents a failure that's going to develop within the spillway, then the breach outlet will show us the flow through this area. But to get the flow coming over the top of the spillway, we want to define an additional outlet device, an additional weir for that flow. So we would actually have 2 outlet devices in many cases. We would have a weir, it could be sharp-crested or broad-crested, for the normal flow over the spillway, and then we would have our breach outlet, and these 2 elevations would presumably coincide. The elevation at where the breach starts to develop should be the same as the crest of the spillway. So that's up to you to coordinate those 2 outlets and make sure they're present. Of course, if you don't have any flow coming over this top spillway and you're just pre-filling the pond to the top of the breach and then watching the breach flow alone, then you would not need to describe that primary spillway in your model. It depends entirely on the exact objectives of the simulation that you're trying to perform. So that's the basics on the geometry and the background on what we're trying to simulate. Let's look next at a model in HydroCAD, which I already have set up with a couple of dam breach outlets. This will just save us a little bit of time in going through these. We have several different scenarios here. The first of these is a timed breach, so it is simply breaching at a specified time. We also have an example of an elevation breach, where we'll trigger when the pond reaches a certain elevation. And we have 2 variations of this. The first elevation breach is using a constant inflow. It makes it a little bit easier to visualize what's happening in the model. And then we'll look at an actual runoff hydrograph coming into the pond, where things get a little bit more interesting. And then finally, we're going to look at tailwater effects. We're going to look at what happens when we take that pond and it's coming into perhaps a downstream reach or a link that's establishing a fixed tailwater elevation. We could also have tailwater generated by a downstream pond. Any of those elements will generate tailwater, and the breach outlet, since this is essentially a trapezoidal outlet device, just varying in time, but it's a trapezoidal outlet, so we can assess the tailwater influence at each time step based on that trapezoidal outlet. So that's just a brief overview of what I'm going to go through here in the model. Let's first just come in and edit this particular timed breach that I've set up. And we've specified that this is a detention pond, that we do have a storage volume here. And I've simply defined a prismatoid to provide the storage behind the dam for this example. On the Outlets tab, we have just 1 outlet device here, which is our dam breach. If we were creating a new outlet device, setting up this pond from scratch, we would just double-click a blank line, and we would come down through this list, and we would pick the dam breach outlet. I've already set up that data, so we can just double-click this line in order to edit the existing information. So let's look at the fields here briefly and see just how this is set up. And you can see how each of these fields corresponds to the illustration that we've just been through. The top elevation is where the breach will begin. So this is the uppermost limit of the rectangular or trapezoidal shape. The bottom elevation is simply the bottom of that shape. And the breach height, the 4 feet, is the difference between those 2 parameters. If you were to adjust the bottom elevation, it would automatically recalculate the breach height, or if you change the breach height, it automatically recalculates the bottom. So obviously those three parameters are interrelated. So that establishes the vertical dimensions for the breach. In the next column, we start with the bottom width. If this were a trapezoidal or rectangular breach, then we would need to specify a bottom width. But if it were just a V, then we could leave the bottom width at 0. Next, we have the notch angle, simply the total included angle between the two sides of the weir. Again, if it's rectangular, that notch angle would be 0. Weir coefficient, a default English coefficient is provided here. You could change this coefficient if you desire. Then in the third column, we have the information that indicates exactly when the breach will initiate and how long it will take to fully develop. In this instance, we've specified that the breach is going to start at 11 hours. So regardless of the water surface elevation in the pond, the breach will start to develop at that point. And it will take a total of 5 hours for the breach to fully develop in this particular example. We could also have specified a water surface elevation at which we want to trigger the breach, and we'll look at that in the next example. But since we're triggering here at a specific time, the starting elevation is left blank. Essentially, HydroCAD will determine the elevation at that time, and that's when the breach will begin. Like all outlet devices, we can set a device routing. We would normally leave this set to primary, although you could change this routing to perhaps secondary or tertiary if you wanted to break out the flow through the breach. This could be handy because it would give you separate reporting of the breach flow in your report. So you could see exactly how much is going through the breach and how much is coming over the standard spillway or through other outlet devices on your pond or reservoir. And there is also a discharge multiplier. This would generally be left to 1. The discharge multiplier is normally used if you have several identical devices or if you wish to adjust to derate or increase the efficiency of a particular outlet device. But for a dam breach, I would imagine that that would be left at 1 in virtually all cases. If you need more information on any of the parameters on this screen, naturally just click the Help button and that will take you to context-sensitive help for that specific screen. This will explain each of the parameters in detail. If you scroll to the bottom of the screen, there is also a link to the dam breach flow calculations. This page talks a little bit more about exactly how the calculations are performed, with a final link to the trapezoidal weir equations. So these are the underlying equations that we're using to calculate the flow through the dam breach. It's just that our dimensions are changing over time. Otherwise, the calculations are the same as if you were to set up a V or trapezoidal weir outlet in HydroCAD. So that is a run through the basic parameters on this sample pond. Now, if we double-click the pond, it'll open up a report window for that pond. And what we're seeing here initially, a couple of things that are notable in the Hydrograph. In this case, we have just pre-filled the pond to a specified elevation. If we come back to Edit and go to the Advanced tab, this is where you can set a starting elevation. So we can have a pond in this case that has no inflow hydrograph. We've just pre-filled it to 104. So that's what we're seeing in this scenario. Because you'll notice down the bottom, our inflow is 0 at all times. There's no inflow coming into the pond. We do, however, have this blue outflow hydrograph, which in this case represents the flow through the breach. Now, to get a better idea of what's going on here, if we right-click this hydrograph, go to Report Items, select Elevation, this turns on an elevation curve. You'll notice the additional legend that appears on the right-hand side, and this axis is labeled from approximately 101 up to 104, and we have an additional black curve for elevation. In order to have that automatically come on with all our reports, we can again right-click, go to Report Items, and Save as Pond Defaults. So now for each of the report windows that I open up, it will automatically display that curve for us. We could always go back in, right-click, and remove it if we want to, or we can just reset the pond defaults if we don't want to see it any longer. So with the elevation curve turned on, let me enlarge this window a little bit and toggle to a 2D view. And now what you can see is that our elevation is beginning here at 104, and that's where we pre-filled the pond. We've also specified in this particular model let's have a look at our summary for a moment. Here's our outlet device. We specified that our breach is starting at 11 hours. So if we come back here to the hydrograph, you notice that we start to see primary discharge here at the 11-hour mark. So that's when our breach is starting to form. And the pond is still at 104 at that time. As the breach develops, we get a greater flow through the breach, and you'll notice the water surface elevation is dropping in the pond during that time. We have specified that the breach is going to develop over a period of 5 hours. Again, if we come back to the summary, we can see develops over 5 hours. And so on the hydrograph, you'll notice that our breach, which starts at 11, will be fully developed at 16 hours, and that's the point in this scenario where we're seeing maximum flow. That's not always guaranteed to be the case. It depends on a lot of parameters, but in this example, the maximum flow occurs as soon as the breach is fully developed. At that point, there's no additional area available for flow, and so with our dropping water level in the pond, the flow through the breach is going to decrease. So that's a simplified example, but it's much easier to see the different elements of what's actually going on the outflow hydrographs and on the elevation within the pond. The other tabs here are worth looking at. If we look at the discharge tab, what this is showing us is a stage discharge relationship for the breach. Now the breach is variable. It's changing over time. So what this graph is actually showing us is that before the breach initiates, when we have no breach area, we're going to have zero discharge. So from an elevation of 100 up to 105, we have no discharge. Then the discharge is initiating, and this is the fully developed condition for the breach. And then if we apply lower head to the fully developed breach, this is the flow we'd have. So this is essentially the rating curve here for the fully developed breach. It's flow versus elevation over that opening. So let's look next at an elevation-based breach. This first one was just based on time. And let's double-click this one. And things get a little bit more interesting here, which is why I started with the simplest case. Now, the first thing to notice here is that in this scenario, we have a constant inflow. So if I double-click this link, we're using the link to generate a constant flow that's coming into the pond. We could generate that flow any way we like, but this just makes it a little bit easier to visualize this example. And so the constant inflow is the green curve that's coming in here. And you can see that the pond initially starts empty, which is our black curve here. So down at the bottom, we're at 100 feet elevation, which is the bottom of the pond. And as soon as we start to get that inflow, we slowly fill the pond. We get a linear increase in elevation for this particular pond. This continues until we hit the trigger point for the breach. Coming to the summary tab, we come down to our breach. You'll notice that the breach starts here at 104 feet of elevation in the pond, and it takes 5 hours to develop after that is achieved. So let's come over to the hydrograph, just take a closer look at what's going on here. So if we look at the elevation curve, our trigger is actually happening up here at 104. So 104 is where the breach begins, and you'll notice that in fact if we come down at that time, which is approximately 18 hours, this is where we start to see flow through the breach. So the initiation has started at 18. It's interesting to notice that the water surface elevation continues to increase for a short while after the breach begins. Because the breach is just small initially, the pond is still filling somewhat. So even though there is somewhat of a breach, there's more inflow than outflow, so the water surface elevation continues to go up for a while. The breach continues to develop, and we've specified that it's going to develop over a period of 5 hours. It's starting at approximately 18, so out here at 23 hours, you'll notice is when the discharge stops increasing. The breach is fully developed and the flow starts to drop at that point in time. And of course, the elevation is dropping steadily in the pond as that occurs. So that's an elevation-triggered breach with a constant inflow. If we come to the editing screen for that pond and go to the Outlets tab, and then here you'll notice we've actually got two separate outlet devices. In this scenario, we have the dam breach, but I've also added a spillway up at the top. This is designed to simulate the total flow over our normal spillway in addition to the flow that's coming through the breached portion. If we come to the dam breach, this is very similar to our previous example, except that now we've set a starting elevation at 104 rather than specifying the time at which it will begin. So what we've done in this model is that we have a breach that's going to extend from 104 down to 100. We're going to trigger when we hit 104, and we also have specified a spillway at 104. So we've actually got some flow here, which is the flow over the spillway, but we also have the flow through the underlying breach. And that's part of what's represented here by this flow hitting 104, continuing to increase as we're getting flow that's coming over the main dam wall. And then finally the breach develops and we get a much greater outflow from the combined total of those devices. And of course we can toggle any of these views over to look at a tabular view if we want to look at individual numerical values, and that's available for each of these tabs. As always, I do advise you to have a look at your summary report rather than just going through the data entry screens. The summary gives you the overview of how all of your input data has been interpreted by the software. And so it will tell you really a lot more about how the model's behaving than just going back through the data entry screens. And in the case of the dam breach, the explanation down here will give you a pretty good idea of what's set up. That the top of the breach is at 104, the bottom's at 100. The breach starts or initiates when we hit a water surface elevation of 104, and then it takes 5 hours to totally develop. Okay, the next example I have here is very similar. That is, it's an elevation-triggered breach, but rather than a constant inflow, we're actually running a hydrograph into this, a runoff hydrograph. So if we double-click our subcatchment, you can see we have an actual runoff hydrograph. We've got 2 acres here that's generating this flow. So if we open up our pond report now, we get an even more interesting and complex behavior because we have a time-varying flow. But the principles you should now understand from these easier examples that we've just been through. If we switch to the 2D view, and then we can even zoom in. If we drag from upper left to lower right, we could zoom in on an area so we can get a better look at what's actually occurring in this model. And what we can see here is that we're hitting our trigger point at 104. We're starting to get discharge at that point. And then the breach is developing, causing this fairly rapid increase in discharge, and then we slowly draw the pond down over time. The green curve, of course, is our inflow hydrograph. We could also come into this kind of model and we could split out our outflows. I believe, yeah, you'll notice we have the spillway and the dam breach routed both to primary. We could take the dam breach and we could route that to secondary and click OK. And now we have a couple of different curves. Gets a little bit more complex to view, but what you can see here is that this gray curve is our total outflow right here. And that is composed of a primary flow, which is the flow over the spillway. So this is the flow that's occurring just while we're up above the 104. And then the red is the dam breach. And you'll notice that takes a little bit longer to develop. And then the gray is the total of the two. So it can be very handy to set separate routing for the devices in order to understand the behavior. When you do that, of course, you will get 2 separate outflow handles that will appear on your diagram, one for primary and one for secondary. Through all of these calculations that we've been looking at here, these examples, a reminder that you do need to use the dynamic storage indication method when you're doing a routing using a dam breach, because we are dealing with a dynamic device where its dimensions are actually changing during the model. The dynamic storage indication method, or DSI, also lets us handle tailwater capabilities, and that's something that we can actually demonstrate in this example. What I've done here is to place a channel downstream of this dam breach scenario. So let's open up the window again for the dam breach, and if we leave that window to one side, and now we come over to our model, and I'm going to take the outflow handle from that pond and I'm going to drag it down to this channel. So at the moment we have free discharge scenario. There's no tailwater effect. If we drag it over, then when I release that, you'll notice the calculation window in the upper left will be updated, and we do see changes in the model. So just to demonstrate that there is a response here to the tailwater. What we've done is placed a discharge channel up relatively close to the breach so that as the water fills in the channel, it creates tailwater on the breach and reduces the flow. We can do the same kind of thing with our other runoff hydrograph scenario. And let's come back here just for simplicity and set both of our outlet devices back to primary. And then if we take the outflow handle from that pond and bring it down, again, you'll see a change. Quite a significant change here in that we have a fixed tailwater elevation that's been defined by this link, just for clarity in this example. And that fixed tailwater elevation, I believe, is at 103 if we come to the summary. Yeah, in fact, there it is, fixed water surface elevation. So what's happening is that with that tailwater of 103, our pond never draws down below that level, exactly as you'd expect. The breach opens up, it empties until things equalize at that point. So just to demonstrate that the tailwater effects are functioning here when you use the dynamic storage indication method. You can have also a pond downstream. That would be another tailwater scenario. So we could have a breach that's flowing into a second pond. That pond might represent a roadway below the dam with a culvert under it and water flowing over and storage above the roadway impoundment. So all of those scenarios can be handled. The only limitation to keep in mind on your tailwater handling is if you have a reach in HydroCAD, that a reach is not tailwater sensitive. A reach always operates under normal Manning's flow conditions. So if you were trying to model a dam breach going through a channel, perhaps with variable cross-sections and complex water surface profile issues, then that's a scenario where you might need a separate model that's designed specifically to handle those cases. So you'll find that HydroCAD is suitable for a lot of different kinds of dam breach analyses, even though it's not based on any one specific other piece of dam breach software. What we've done here is we've added a new outlet device that functions within the existing framework of HydroCAD. So we're not attempting to replicate, per se, anyone else's dam breach results, although if you look carefully at the analysis, as long as you're staying within these constraints, you should get very comparable results between HydroCAD and other tools. You just need to keep the specific capabilities of each model in mind as you compare the results between them. So that's a general look at dam breach routing. The tailwater effects, reach routing, and other capabilities. If you've got any other questions about this, certainly contact us at hydrocad.net, support at hydrocad.net, and we'll be glad to answer any questions you may have. And it's very easy to set up a couple of these scenarios in HydroCAD and see how they behave yourself. If you want a broader overview of HydroCAD outlet devices, we do have a previous session recorded, session 312, I believe, which covers the full spectrum of outlet devices that are available in HydroCAD. And so you can use that for an overview, and if you just want a brief coverage of dam breach routing, that will do it for you. Otherwise, we will be posting the full recording of this session later today, so it will be available for you or others that may have questions. So So that's really all material I wanted to cover today. Thank you to everyone for joining us, and I hope you'll join us at a future session. Thanks, and have a great day.